thank you. So let's go to a new topic, common source amplifier. On the left, I claim that this is a common source amplifier. Let's look at it, what it means, right? Whenever you are given a new circuit, right, although it's not new to you, you need to look at it and understand every component first. Don't just jump in, dive in, and then start doing the equation. It won't help, right? So I see I have a transistor. Is it NMOS or PMOS? Yeah, I know that this is NMOS because the source is pointing out, the arrow is pointing out, or someone told you that, or you are the circuit designer. So good. So from there, I know this is drain, this is source, this is gate, because drain is at higher potential. I see that my drain is connected to something called output. This is given. We decided to make this as the output, and to our resistor, and then to the VDD. We also connect the gate to Vin, so this is the input, right? So it is very clear that I have the input because it is given, right, at the gate. I have the output at the drain. I'm a little bit worried this might not be safe. Let me escape and, okay, it is safe. Okay, so input is gate, output is drain. When you have an input and output, you need to refer to a common place. For example, I'm at 10 meter. My height is 10 meter. Your height is 20 meter, your elevation. That means we are referring to the same ground, right? Because if I'm standing on the top of the mountain, and when I say it is 800 meter, it refers to the sea level, right? So you can refer to different level. So you should have a common ground. That is the point of the circuit, right? Everything refers to the same location. So that's why here you see that the source is connected to ground. When you say your input is 1 volt, it means you're referring to ground as 1 volt. It means because source is connected to ground. So that's why it is common source, because they all refer to the source potential. Is that okay? You have 3 terminals. 2 of them, one is input, one is output. They all refer to the source potential. That's why it's called common source. Source is common to that, okay? So let's see. So outside this circuit, the first thing I need to play with that. So let me see if my Vin, right? For example, it goes from 2 volt to 2.01 volt, right? It means the, sorry, let me redo it. That is not a good way to draw it. What I mean is, for example, if Vin increase, for example, if from 2 volt to 2.01 volt, right? I want to understand what will happen to this circuit. Now, this is a transistor. Naturally, when I increase the gates, you will think about how much the drain current will change, right? So what will happen to the drain current? What will happen to ID, which is this one? What will happen to drain current when I increase the gate voltage? Yeah, it will increase. So it might go from, let's say, 1 milliampere to, let's say, 1.01 milliampere. Why is that? Because ID equals to W on L mu C ox divided by 2 VGS minus VT squared. So I increase the VGS, which is Vin, then ID will increase, right? So very simple. But if I ID increase, what will happen to my V out? maybe you will get confused, but then how do you get V out? Very good, larger drop. Because V out equals to VDD minus IDRD, right? This is fixed. You have more current, so you have a larger potential drop. So V out will reduce, right? So it might change from, let's say, 3 volt to 2.9 volts, for example. Is that okay? Everything normal for you? That is what you need to do when you analyze a circuit. Okay. What is the gain of this circuit then? What is the definition of gain? It's not rocket science. You invest $100 in the stock market and you get back 110. What's your gain?
10%.
Someone say 10%, right? That's okay, yeah. Or you can just say I want to find just the gain, the ratio. 110 divided by 100, right? Output divided by input, right? That's it. So what should be the gain of the circuit here? I mean, definition. V out by V in, right? But the only thing is that I want to make sure that is the change of V out divided by change of V in. Okay, because we're talking about small signal. Okay, you can say, well, it is 2.9 divided by 2.01, but that is not the gain we are interested in. I want to see the change, right? So what is the change of V out? Just follow the definition seriously, strictly. 2.9 minus 3, not 3 minus 2.9, because it changed from 3 to 2.9, so the change is 2.9 minus 3. When the input changed from 2.2 to 2.1, I mean 2 to 2.01, right? When my input changed from 2 to 2.01, the gain changed, the output changed from 3 to 2.93, right? So what is this? Negative 0.1 divided by 0.01, the gain is negative 10. Right? That is the meaning of the gain in your small signal. And you should actually understand this first, right? Before we go to small signal. That is the meaning. And again, you look at a large signal, I mean the total signal. It's still just playing with 2 volts, still positive. The output is still positive, so you should not be surprised to see negative gain because we're talking about the change. Right? It's not saying that I input 1 volt, I get a negative 10 volt. It's impossible for this circuit, right? It will go to off state or linear mode or whatever. Okay? So have this understanding first, then the rest is just the math. Okay? So this is an overview. I hope that whenever you have a new circuit, you will try to understand from this perspective. So now our goal is to use small signal to find out all the quantity we are interested in. This is the same circuit I show you, right? So again, this is the gate, this is the drain, this is the source. And now we cannot just use the hand waving way. This is very useful intuitively, but now we want to do it rigorously, right? So what should we do? We should draw the small signal model. How do you draw it? As I told you last time, right? Draw a box across all the transistors. And then I'm going to replace this one with the circuit from my cheat sheet. This one, I call it VGS. This will give me GM, VGS. And this is R0. This is gate, this is drain, this is source, right? Make no mistake on this part. And after that, you try to look at the source is connected to ground. Do you see that? The source connected to ground, so I make it to ground. Is that okay? How about the gate? It's connected to where? Nowhere. We just call it V in. Right? How about the drain? Connected to RD, and then it is connected to the drain connected to RD, and then eventually to VDD, right? Did I make any mistake? I connect it to the ground. I say this is correct. Why this is correct? Why I can connect the VDD to ground?
In small signal analysis, you don't have a VDD.
Yes, because it's small signal analysis, and you said that because this is DC, so this is AC ground. Remember, we have two things. One is you draw the model. Another, you short all VDD, short all VDC, and open all IDC. All the constant current should be open. All the constant voltage should be shorted. That I get this one, right? You know this already. You learned that before, right? So now I will start look at R in. What is the input impedance by definition? What else can you do for input impedance? We apply a voltage, V in divided by I in. That is the input impedance, right? But last time I told you it has an important definition that you need to make sure I out equal to 0. Means there's no loading, it's open circuit, right? Indeed, by default, this is open circuit, right? This output has no loading, no extra loading, right? Otherwise, you need to disconnect it, yeah. So, what is this? We are in divided by I in. Looks tricky, but let's just apply 1 volt to it. What do you get for current when you apply 1 volt to the input? Nothing. Right? For example. So it is infinity, the input impedance. Right? There's no way the current can go through. Is that okay? How about the R out? Now then we need to again follow the definition. What is the definition? V out divided by, so for this one, actually, I want to use different color. V out divided by I out when what? What is the V in equals to 0? Thank you. Right? So in order to do this, I'm going to do this. I'm going to apply V out and then measure the I out. But I will need to short. I will need to short this one to ground. Right? I need to apply V out to get I out, and I need to short the V into ground by the definition. So when this is ground, what is the value of VGS? 0. Then what is the currents going through here? Also 0, right? Because it's GM times 0. VGS is 0. Right? So now you can use KCL to find out what is the input impedance. But you are smart enough, right? Look at this. What else can it be? I only see 2 resistors in front of me. And then what can be the resistance of the resistor? It must be the resistance of the resistor, right? So what is the resistance of the resistor here? Exactly. RO parallel RD. That is exactly what I see. There are 2 paths in front of me. Left is RO, right is RD. The total resistance is RO parallel RD. If you don't like that, use Ohm's law, KCL, KVL, whatever. You should get the same thing. So that is the output impedance of the common source amplifier, right? Now, how about the gain? To get a gain, then we need to use another circuit. I mean, I try to make this easy for you to study. So let me redraw it one more time to get the gain. This is V in. And this is GM, VGS, and I do this. I call this R0 parallel RD. And this is VO. Is this okay? I just combine them together, right? Because the effects of this one, because they share the same terminals, is just equal to R0 parallel RD. If I have 100 ohm here, 100 ohm here, the effectively this is 50 ohm. I just say that I have 50 ohm here, right? So now I will need to use KCL. This is a little bit troublesome. How about let's go through this route? Is it, yeah, KCL, right? So I have GM, VGS, which is the current going through this voltage control current source, equals to what? Equals the current going through this resistor. Can you tell me what is the current going through R0 parallel RD? Ohm's law, right? So what divided by what? What's the current going through the resistor? He says 0 minus V naught divided by R naught parallel RD. Very good. I'm so glad that he said 0 minus V0. Including myself, I will just jump in and say it is V0 divided by R0 R parallel RD. Because I thought that the potential across it is V0. But unfortunately, we need to be very careful because the loop we are drawing is going in this direction. When we see this current equal to this current, it's talking about the current going down here equals to the current going up, not the current going down, right? So if that is the case, I must do the beginning potential minus the ending potential. So it must be 0 minus V0. But this is a mistake we often make. So you need to be very careful. Okay? So with this now, it will be easy. What is VGS? Can we be careful again? What is VGS? What is VG? V in. What is VS? 0. Again, we are very careful about this. Okay? So with this, I have V out, I have V in this equation. So the gain, by definition, is V out divided by V in, which is equals to negative GM R0 parallel RD. This okay? Now I spent doing very slow, right? But the main point is that you need to be very careful about the step. Then you won't make mistake. If you are not careful, you might get positive gain. Okay. So how about let's look at channel length modulation. What is the point of channel length modulation? When we are talking about this large signal, right? We see that the gain is increased by negative 10. Now you say there's a channel length modulation. What exactly happened? Let's repeat what we said before. For V in increase, when the V in increase, for example, again, it goes from 2 volt to 2.01 volt. Fine. Then last time you told me that ID is going to increase. It may go from 2 milliampere becomes 2.01 milliampere. That's okay, right? That's what we discussed just now. And then what happened to the output? Well, it will decrease because of the potential drop. So that's why you get maybe from 3 volts to 2.9 volt. Is this okay? That's what we said just now, right? However, when your Vout decrease with channel length modulation, do you remember ID equals to W on L mu C os divided by 2VGS minus VT square times 1 plus lambda VDS. When you have channel length modulation, you have this extra VDS, correct? So when my Vout reduce, it means the VDS reduce. What will happen to the current? What will happen to the current? When the VDS reduce, what happened to the current? It should reduce, right? So because of channel length modulation, your current actually may be just, instead of going to 2.01, you may just increase to 0.05 milliampere. Okay? So as a result, your Vout actually just will not reduce as much because your current does not increase as much. It might just change to 0.25 volt instead of 2.95 volts instead of 2.9 volt. You get 2.9 volt because you have a substantial increase in current. But once you reduce the gate drain voltage, your current actually does not increase as much. So your potential won't decrease as much, right? So that is the problem of the channel length modulation. And as a result, the gain is going to be, in this case, 2.95 minus 3 divided by 2.01 minus 2. This is just negative 5 instead of negative 10, right? Of course, this is a toy example. All these numbers are just fake, right? But do you see why the channel length modulation is reducing the gain? Right? It's because when I increase Vin, Vout will try to decrease the loss. Then I have a large gain, right? Negative gain. But because when I reduce the VDS due to channel length modulation, my current actually does not increase so much. So my Vout cannot reduce as much as I want. So you get this channel length modulation. And it is reflected in this resistor. Now you look at the gain, it's GM times R0 parallel RD. What is R0 when there's no channel length modulation? What is R0 when there's no channel length modulation? Forgot? Infinite. So it becomes only GMRD, right? If you have a resistor in parallel, it reduces the total resistance, right? So that's why when you have channeling modulation, you actually reduce the total resistance here. So your gain reduces. So I just want to bring you to the attention to this. Is that okay? So let's do some example. This is a common source amplifier because it is in this set of slides. But you should check it. You find that the Vin is a gate, the Vout is a drain, and the source is a common. So it is common source amplifier. And because of this, I can use the equation I have learned. I know the gain equals to negative GM R0 parallel RD. You don't want to derive again in your final exam, right? You have this in your cheat sheet or you memorize it. What is GM? Now we need to find an equation to get the GM. From here, which equation should I use? Then you look at what is given to you. Should I use this one? Right, I have mu C os, I have W on L, but do I have VGS? Is VGS given? No. On the other hand, ID is given, right? So I'm going to use this equation, right? So GM equals to square root 2 times mu C ox, which is 100 micro, times W on L 10 over 0.18. And then what is ID? 1 minute, right? So from there, you just plug in. I think I got 3.33 minutes Siemens. Okay. So what else do I need? I need RO and RD, right? What is RO? Based on the information given here. Infinite, because lambda equal to 0, so no channel length modulation. But if you forgot, just recall this equation. Yeah, lambda equal to 0, so infinite. Very good. So then I can ignore it, but I do have RD. So the gain equals to negative 3.3 millisiemens times infinity parallel RD, which is 1 kilo ohm. Anything parallel infinity is itself, right? So this is negative 3.3. And what is the unit of the gain? Unitless. So I think I'm correct, right? Because Siemens and ohm will cancel each other. So here I actually better just don't write it because I did not write the ohm. Right, so here you see that we first spend a lot of time to derive the equation, and you know it's rigorous, and you trust what you have derived. Then in the future, you will just, oh, somehow this GM is gone. In the future, you will just use this equation to do some more complicated calculation, okay? Now, okay, I still need to show the simulation.